Welcome to the second episode of Real Analysis. Today's objective will be to introduce max and mins of sets. Looking at the definition, we see that the definition for a max versus the definition for an upper bound have similarities. For example, they are both greater than or equal to every element in the set. So the main difference is that a max needs to be in the set, whereas an upper bound doesn't need to be in the set. It just needs to be above the set. The easiest way to see a max is to use a closed interval. Consider the interval from -3 to 3. We see that the largest element in the set is 3, so it must be a maximum. Next, we'll prove that this set has a max of 7. First, we'll do some scratch work to learn why the max will be 7. Further, we can see visually that the interval we discovered will have a max of 7. For the proof, we'll start by showing that 7 is in our set A. Then, we'll pick some arbitrary value within A and use our scratch work to show that 7 will be an upper bound of the set. Since we showed that 7 is both in A and is an upper bound, we satisfy the conditions for 7 being a maximum of the set A. Similarly, we see that the definition for a min is parallel to the definition of a lower bound, with the exception that a min must be in the set, just like the maximum was. From the same interval as before, we can see that -3 will be a minimum for this interval. Now, we'll prove that if some set A has a minimum of 6, and B is defined as such, then B will have 2/3 as its minimum. Once more, we start by showing that 2/3 is in B. Then, we pick an arbitrary element in B and unpack the definition of what it means to be an element in B, which relates back to the set A, which we know has a minimum of 6. We use these facts and some algebra to show that 3/2 is a lower bound of B. Since we showed that 3/2 is in B and is a lower bound of B, 3/2 fits the definition to be a minimum of B. For our last proposition, we'll prove that the open interval from 1 to 2 has no maximum. Since we're showing something is not something, we use contradiction. We start by assuming that the open interval from 1 to 2 has a max, call it M. We then use the definition of a max to say that M will be greater than or equal to any number in the open interval from 1 to 2. Further, we know that M is in the open interval from 1 to 2 since it is a maximum. From the definition of an open interval, we can say that M is strictly between 1 and 2. Now, we consider n plus 2 over 2, with m strictly less than 2. From this, we can get these inequalities, since the only difference for the top inequality is the 2, was replaced with an m which we know is less than 2. The second inequality holds by the same logic. This gives us this chain of inequalities demonstrating that m plus 2 over 2 is in the open interval from 1 to 2. However, this is a contradiction, since m can't be strictly less than m plus 2 over 2, and greater than or equal to m plus 2 over 2, at the same time. Thus, the open interval from 1 to 2 has no maximum. That's all for today. Thank you.